I find myself being more and more frequently to be one of the persons who knew the people being celebrated as one of the first ones. In fact, I have to go back about 50 years, so I will ask you to forgive me when I skip over certain things, but I have to cover 50 years. And I think I knew Alan before he had a beard. So that dates me. The reasons for Alan's success is that he is a multi-talent. He works on instrumentation, he works on theory, on observation and interpretation. And I think that is the theme which we will see in going through this journey from fusion to space. I start with the 60s and would like to show you the future-oriented 2-meter grazing incidence spectrometer which he built. And then I will go quickly over identifying spectral lines in the laboratory, comparing them to solar spectra. Forbidden line in helium-like ions I will skip, only mention, and also satellite transitions. They will be covered later on in this meeting. Now, the instrumentation, Alan built, published at least in '65, he published a paper on a 2-meter grazing incidence spectrometer, which was both photographic at that time, of course. Xerox machines just made their inroads into university labs. So that was very, very early, but it was already photographic and photoelectric. It was gravity independent, which predicts a little bit the behavior in space. And it had pressurized electronics, which was at that time also something which one did. It's the instrument, the light comes in here. There's the entrance slit, the grating, the exit slit, the detector, and the pressurized electronics. And because it is in vacuum, the electronics were pressurized. That was time when one had photomultipliers with high voltage. And then there is a screw and the nut to drive the exit slit, and of course the second screw drive, which then makes the detector follow. So this was a magnificent instrument at the time. However, he needed a suitable spectroscopic light source, and that was the zero-energy toroidal assembly. This was a tool for fusion. Thought to be for fusion, but they used it as a spectroscopic light source, and they used it to identify the solar spectrum in the extreme ultraviolet or soft X-rays. Now, this is a spectrum of zeta, and of course at that time one didn't have tables which gave all the wavelength. So what did one have to do? One could identify those lines after one identified them with the aid of isoelectronic sequences and by observing the non-crossing rules. In this example, which is the potassium sequence, we can see that we have a 4F doublet F state and another 3 doublet F state, and they cross between vanadium and chromium, between these ions. And of course, if they have the proper symmetry, they will mix with each other and repel with each other. So one can, if one scales the ordinate properly, one can see those things more in detail. But that's the way how one made these identifications. I think Brian will probably come back to that later on. Now, this is the solar spectrum, and what they did was that they used the zeta machine in a proper configuration where they got quite a bit of iron lines out of the stainless steel, and what they got was this spectrum which had the lines in zeta which they could identify and could compare them directly with the solar spectrum. So that was in '63, also to get together with Brian Fawcett and Bob Wilson. I skipped dielectronic combination, but instead of that, I would like to show the picture of Alan Burgess, who did much work in this field. And In fact, that was also very important for the ionization equilibria of the extreme ultraviolet for the space observations, because the electronic recombination sometimes changed the abundance of an ion by a factor of 2. And at that time, he also collaborated very much with Carol Jordan. I remember this is a picture of the time when we fought again about the wisdom of using F-values from astronomical observations rather than laboratory F-values. But she made a fantastic career and is now Dame Carol Jordan, and is obviously very pleased. Now I come to the 1970s, and there was an Eclipse rocket in March 1970, and Alan followed this up. This went then the interpretation of the Lyman alpha corona, and he then developed also a model of the chromospheric network. Then that gave the idea for CHASE, and eventually that gave also the idea for the GRIST mission and the two SOHOs, which led to ESA's Horizon 2000 in the 1980s. Now the Eclipse rocket was quite the thing. In March 1970, the umbra of a total eclipse went over the NASA launch range on Wallops Island, where they launched rockets from. And then a consortium of groups from Imperial College, Harvard College Observatory, the Column, and the York University Toronto, usually by Reg Garten summarized as the club, decided to construct a slitless vacuum spectrograph and launch it from Wallops Island on a flight through the umbra. Now this was quite a feat, because you have to not only launch a rocket complete with everything functioning, but you have to launch it at the right time, in the right direction, into the right place, and also pointing at the sun, of course, but also flying through the umbra in the appropriate way. So this was you see the ideal path, and you see the actual flight path, and you see the flight plan. Now the data taking started there, and the data taking terminates there. So that's why the payload goes through the rest frame of the umbra, presented here through the rest frame of the umbra. That was, of course, then published very quickly, and Bob Spear was actually the person who did most of the project, and he was deservedly the first author. But Alan later on looked at these spectra in depth, and he found the big surprise, which was the corona around Lyman alpha. So that was the biggest surprise, because how would you have a Lyman alpha corona with temperatures of several millions of degrees? But Alan, I think, was the first one to really find this out. And he looked at the various possibilities. Thomson scattering by coronal electrons, that wouldn't work, because the image would be smeared out, because the electrons are too fast. Small angle scattering by the F corona, that was, if one extrapolates that from the visible, that gives a signal which is about a factor 10 to the 5 too small. Electron impact on neutral hydrogen, where there are about 10 atoms per cubic centimeter in the corona, that is 10 times too small. But the fluorescent excitation of hydrogen by chromospheric Lyman alpha, that gave the actual explanation. So he found that out rather quickly. And indeed, in the year after that, after the rocket was flown, Alan appeared as the first author of an article in Astrophysical Journal, which describes the entire mission and the proper interpretation of the Lyman alpha corona. But then there was a plan for a second Eclipse rocket to be flown out of Mauritania, but that rocket actually did not succeed. But Alan came to the Harvard College Observatory, because at that time Skylab was already flying. And in preparation for this rocket flight, he also looked at the data of ATM. And with the ATM data, but of course also with the results from the first Eclipse rocket, that led to the chromospheric network, both for quiet solar areas and for coronal holes. Now, not many of you remember Skylab, which was a mission with 3 crew, and it was made out of old Apollo hardware. And you see there a circle with solar panels. That was the ATM. That was a barrel filled with instruments which all were looking at the sun. And the astronauts lived in this upper stage of an Apollo rocket. The whole thing had almost a failure because one of the solar panels fell off together with the shield for micrometeorites, and therefore one had to make a little curtain here. Astronauts actually mounted this little curtain so that this thing was flying. It was visited 3 times by astronauts, and it had an enormous wealth of data. Most of them photographic. That was at that time still possible because we had the astronauts. But the Harvard instrument which he used had photoelectric detection. And this is just an example of the quality of the data of that time. This is a 5 by 5 arc minute raster with 5 arc second pixels. And you can see the network in the various lines which go from Lyman alpha to the coronal line of magnesium-10 with increasing temperature like that. And you see that the network does change from one to the other, but it changes mostly then in the corona. But there was also, and I'm happy to say that I was involved in that too, one could also take rasters along the limb of the sun. It's an assembly of 5 arc minute rasters. And one could see that in Neon 7, which is a transition zone line, the limb was much higher. And that then is reflected in Allen's model of the chromospheric network, where you see on the one side you see the one in quiet regions, and you see the other one in coronal holes. Of course, many of you will remember that coronal holes at that time was, besides black holes, was the main thing of astrophysics. So this was a tremendous step forward. Now I come to the 1980s, and there was the question of would there be a solar satellite mission for ESA? We had the solar maximum mission, and Esther will tell us about that. Then out of the Lyman alpha corona came the idea of why not looking at helium in this corona as well, because then one could determine the helium abundance not quite easily, but one had a good chance of determining it, at least in the corona. And then we go towards SOHO and Horizon 2000 and the Venice meeting in May 1984. Now, Chase was with the Space Lab 2 crew. We see a photograph of the people with Diane Prince in the front row. Alan, he had already a beard at that time. And the NASA project scientist Gene Urban, and in the background, George Simon, Lauren Acton, Carl Hinias, and Bruce Patchett. And I think it's appropriate that I also show a second picture of Bruce, because he was very much involved in the Chase mission, and he was also, I remember that he was sent by Alan for the first discussion on our proposal for a SOHO mission, because Alan was at that time chairman of the Solar System Working Group, and he felt it was better not to be involved in the mission, which should be approved by his group. Now, how SOHO came about, that's my last things I want to tell you, because many of you may not know. In 1982, SOHO was proposed as a solar high-resolution observatory in low Earth orbit, because there was a second mission in competition already quite ready for approval, which was called DISCO, which was around Lagrange point 1. But Ernst Rendlenburg, who was the director of science at that time, advised us that we should include a particle payload, which of course did not make much sense in low Earth orbit. But this was a strong community, and Trendelenburg, with his political sense, thought that this was the right thing to do. But then in 1983, after ISO had been preferred over DISCO, SOHO could be changed, and it became the Solar and Heliospheric Observatory in Lagrange Point 1, where it could really make good observations of the solar wind, of helioseismology, and of course also of the extreme ultraviolet. And what happened in 1984 at the final meeting of the Horizon 2000 Survey Committee in Venice, I will tell you now, and I think Geneviève will come back to that as well. But this is the assembly of people who, there was a survey committee and topical team chairman who attended this last meeting, a beautiful site in Florence, in Venice. And key persons there were, of course, Alan Gabriel. He had a beard already. It was Leon van Hove, who thought that after the presentation of the Solar System Working Group, he thought that was much better than the Astronomy Working Group. And he felt that the asymmetry which was in the original program, which I will just show, was not proper. And of course then Bengt Hultquist, who is a strong supporter of solar system, supported all that. Guys supported it, Kirsten Fredka, etc. And actually what had happened was that the executive presented us with a long-term program consisting of 3 cornerstones, 2 astronomical ones and 1 planetary one. And that, of course, was somewhat out of balance. After our presentation and also the remarks of Leon van Hove and others, we could introduce a 4th cornerstone, which was the Solar Terrestrial Science Program, one of its names, and which contained SOHO and cluster. And in this way, SOHO was in the long-term program as one of the missions to be pre-approved in some way. And so SOHO was constructed, and Alan can enjoy SOHO, the pick of the day, of the week, a picture. So with this, I would like to end. Thank you very much.
Are there questions or comments? Yes? No?
Can I make a comment?
Yes, I will get you the microphone. Yes.
No, it's just to point out that Martin has been very modest, because this last maneuver that got SOHO into the Horizon 2000 was largely the responsibility of Martin.
Thank you for the flowers.
Who ran one of those committees.
You are talking about maneuvers. There are maneuvers in these committees. That's a bit surprising. Okay. Thank you very much, Martin, for this comprehensive and, well, very, perhaps too short review. Thank you very much.